Okay, let's see, time to get started. Yeah, so last time, this is where we left off. So we were talking about how to do parametric surfaces. We talked about what is a parametric surface, and I showed you several examples of tools for creating parametric surfaces. So I think I have just the one more to show you, if I remember correctly. Yeah, so sometimes you have an existing parameterization. And what you want to parameterize is not that different, just kind of a tweak of what you want to parameterize. You may recall we saw a version of this back when we were doing parametric curves. So this is a highly analogous idea. I'm just going to show you an example of it. So let's think about the unit sphere. Now, of course, the unit sphere is easy to describe in any of several different ways, such as these two right here. And we've talked about how to parameterize using the spherical graph parameterization. So again, you just write down the regular old spherical conversion formulas and plug in that formula for rho wherever it goes, and that results in what we see here. This is a parameterization of the unit sphere. Okay, now I could write this parameterization in equations. This is all the same thing. It's just writing it out one equation at a time. Not really doing anything there. Okay. All right, so the question I'd like to entertain is, what if I want to look at the ellipsoid? Right, now that ellipsoid is not the same as a sphere, but it's got a very similar equation, right? You look at these two equations, they're not that different, and we talked in the past about how you can tweak equations to turn a surface into a similar surface. And in particular, if we want to stretch it out, right? If I want to stretch it so that instead of having a radius in the x direction of 1, if I want to have a radius in the x direction of a, right? Then what you do is just everywhere you see an x, you replace that x with x over a. Right, and then likewise, you replace y with y over b, et cetera, et cetera. Okay, so that gives us this equation of the ellipsoid. How then do I parameterize the ellipsoid? Well, honestly, kind of the same thing. Just everywhere you see an x, replace that with x over a. Same deal. I mean, after all, the sphere is parameterized by, in fact, a set of equations. That's what this is, just a bunch of equations. Okay, fine. I tend to write it in kind of a vector form most of the time for, convenience, maybe. But it is, in fact, just a bunch of equations. And this is how you stretch out when you're looking at an equation. Likewise for the y, likewise for the z. So this then gives us a parameterization of the ellipsoid, and of course you can rewrite that back in vector form like so. Okay, now this kind of suggests a different take on this, different way to think about the process, which is, notice that our formula for x, here's our formula for x, here's the new formula for x, and let's think about what happened to just the formula that tells me what x is, right? Well, what happened is that formula got multiplied by a. And I'm going to propose that that's pretty believable. If x was this, and then I stretched it out to make x a times as big, well, check it out, there it is. I just literally made it a times as big. So take your pick on which way you prefer to think about this. They both have their moments, right? You can think of it as replacing the variable, right? Or you can think of it as literally adjusting the formula for that variable. The same effect, different sort of aesthetics. Okay. So punchline, if you have an existing parameterization like that, and you want to deform it, right? The way you deform it, so for example, by stretching, is either of these two methods that we just talked about. Okay. So, Another tool for the toolbox. What do you think? Everybody all right with that? Cool. Okay, so there's a bunch more examples in the book. Here's the problem. The book's examples all fit into a form that I think leaves a little something to be desired. All of the book's examples start with the parameterization. They're like, hey, here's a parameterization. And then they try to reverse engineer what is the surface that this is a parameterization of. And that's fine. That's an important thing to be able to do. You do need to know how to do that. And so those are nice examples in that way. My experience has been that most of the time, that's not the order that you need. Usually, it's that you start with a surface given to you in some other form, either described geometrically, right, like I did here. Here I said surface, unit sphere, right? Or maybe it's described with an equation, right? Something like that. So you usually get some description of the surface that isn't a parameterization and what you need to do. And again, my experience, day in and day out, what are you going to be encountering in the real world, as it were, of engineering, is trying to create parameterizations. So you'll notice all the examples I showed you fall into that latter category of how to create parameterizations, not how to interpret parameterizations. Okay, that's just to balance it out. Okay, so this next page is what I'm going to call a luxury. And I'm going to say it's a luxury we can't quite afford, and I'm not going to cross it out. I'm not going to say that you don't need to know it. This is perfectly readable, though, and I think it's, if you read this on your own, you can make sense out of it to the extent that might be necessary. So I'm going to not talk about this page here in class. I'm going to skip right down, though, to what the punchline is, and starting on the next page, then. Here we have a parameterization of the sphere. And nothing important about this being the sphere specifically, but just as a for example, here is a parameterization. And the big idea is when you have a parameterization, one point in the parameter space goes to one point on the surface. Right? And then you can also talk about vectors, right? So this little vector right here, representing moving in the phi direction. As you move your parameters in the phi direction, well, that's going to cause movement on the surface, right? And then likewise, if you move in that direction, that's going to cause movement on the surface. And then likewise, I hope this is believable, if you have a little piece of area in the parameter space, you can talk about the resulting, oh gosh, I have to choose a color. Is red too close? Let's see if red looks okay. I think that'll be all right. There's a resulting little piece of area on the surface. And again, you can ask the usual question, right? We've asked the following question a bunch of times in a bunch of different contexts. If I look at the output size and if I want to compare that to the input size, right? What is the relationship between those sizes? What is the factor by which this area, in this case, gets stretched out to become that area? And you can even probably kind of see how this is going to work roughly. I mean, this is roughly a little bitty parallelogram. It's a parallelogram in 3 dimensions. We have a formula for how to write down the area of a parallelogram in 3 dimensions. This goes back to Chapter 1, arguably goes back to Math219, and it's the magnitude of the cross product of the edge vectors. And so that is going to be the main part of the argument that goes into developing this, what I'm going to, as usual, call stretching factor, right? The factor by which this input area gets stretched out to make this output area. The formula for that stretching factor is this, as it turns out. Again, details on the previous page if you're interested. So this is going to be an important tool for us, and I'm going to do about like this. I'm going to rewrite this formula by making an observation about this expression. And this expression right here is a cross product. Right? Let me scroll ahead momentarily. I'll come back in just a moment. But it's a cross product of the two partial derivatives, and the two partial derivatives are going to be tangent vectors. And again, you can look at that page that we skipped over if you want some discussion of why I know they're tangent vectors, but they're tangent vectors. So if you think about it, if you have two tangent vectors and you take their cross product, the cross product is going to be perpendicular to the surface, and otherwise known as a normal vector. And so because it's a normal vector, I hope it's no surprise. I didn't really quite squeeze this down enough. There we go. I hope it's no surprise that we use the letter capital N to represent that vector, capital N for normal. Okay. And so our formula then for our stretching factor, and remember our stretching factor is, how much does this get stretched out to make that? That's not a very good arrow. There we go. That stretching factor, I can rewrite then. It's the magnitude of this normal vector, capital N. All right. So, turns out this vector is really important. We're going to do a lot of stuff with this vector. Thus it's important for it to have a notation. Capital N is a pretty common choice for what to call it. I think an important observation has to be made about something fundamental to its nature, and that is, you can see it right here in the formula. This capital N comes from the parameterization, right? We have this initially, right? We have this parameterization that takes parameters, gives you points on the surface. That parameterization clearly influences what that capital N vector is going to be. If you take a different parameterization, you're going to get a different capital N vector. Right? And what capital N vector you get clearly matters, right? Because its magnitude is the stretching factor, and so that means something. That's going to affect how we do business on that surface. So anyway, because this comes from the parameterization, I think it's a reasonable choice to call this not just a normal vector, but this is what I like to call the parametrized normal vector. I think it's a pretty reasonable terminology. Now, I will point out, our book makes a different choice. Our book calls this the standard normal vector. It's just terminology, whatever, right? Here's my quibble. If you call it the standard normal vector, it kind of makes it sound like there's something intrinsic to the surface about it. And it's not. It's not, right? Again, it depends on the parameterization. There's lots of ways to parameterize the surface. So they can't all be standard, right? So now I think the counter argument would be, well, it's standard to the parameterization, right? But but I think it remains that, that's a justification, but that doesn't remove the confusion. I still think there's a potential for confusion with this term. So I'm not going to be using this term. You may see it elsewhere. It doesn't matter. That's fine. I'm going to be calling it the parameterized normal vector to emphasize unavoidably that this depends on the parameterization. All right, and that's going to be very important as it turns out. All right, let's see here. There we go. Okay, so let's do a calculation. We're going to compute the area of the unit sphere. Not that we don't already know the answer to that. Not that we don't have other ways to do that. Right? Y'all may have seen calculations in single variable calculus classes, for example. There's some pretty cool calculations that you can do to compute this area. But this is an opportunity to use our new tool, and so that's why I want to do this. And roughly speaking, broad stroke, the way we're going to compute the area over here is we're going to break it down into little pieces, little pieces of area. Right? We're going to relate those little pieces of area, again, no surprise, I hope, to little pieces of area over here. Right? And we're just going to look at all of the parameters that give rise to our surface. We're going to look at each little piece of area here and see how much does it get stretched out to make area over here. And then we're just going to add up all these little pieces of area by effectively keeping track of how big they are in terms of phi and theta. So clearly the first thing that we're going to need to know what that stretching factor is. We're going to need to compute then the magnitude of capital N. So let's take a deep breath and plod through this. I'm going to leave most of the details for y'all, actually, and this is a healthy exercise. You want to make sure, you see how much trig there is? That's a lot of trig. Right now, it's just trig, but it's a lot of trig. Okay, so make sure that you're good with all the various little steps here. And of course, once you have your parameterization, which we've already talked about, that's the unit sphere parameterization, right? Well, you know how to take partial derivatives. Make sure you can do that. You know how to take a cross product. And you know how to compute a magnitude. Enjoy. I know it's a lot of details, but that's the nature of the beast. And again, important to make sure that you can appropriately plod through all of those details. And let me say that differently. It's also important that you can do it yourself, right? Because on exams, etc., you're going to need to be able to do this kind of thing. Okay. By the way, I will throw out a little quick hint. I mean, you look at this cross product here, and that does look like a monster, right? It's a scary looking vector. But check out its magnitude. Its magnitude is just sine phi. That's shockingly convenient looking. The way you turn this ugly vector into a very satisfyingly simple magnitude is by using Pythagorean identity. The Pythagorean identity kicks in several times, and just the simplifications, totally awesome. It works out really nicely. Okay. Again, healthy exercise. Make sure you do that. And so this magnitude is ultimately all we needed. The magnitude of the parametrized normal vector. And as we promised, if you want to add up all of the little pieces of area, each piece of area is stretching factor times parameter space areas, d phi d theta. Right, we're interested in the whole sphere, and over the entire sphere, phi and theta vary like so. And so that's just adding up over the entire sphere. And check it out, we end up with actually a pretty straightforward integral, totally doable, and there's your answer. And I presume that y'all probably recognize that result, again, probably from high school geometry class or single variable calculus class or whatever. Is everybody okay with that? Cool. All right, so again, so back to this summary page. This is kind of all the players in the little story that we just discussed, kind of generalized, not on the sphere, but on just a generic surface. When you have a parameterization, you have your input parameters, S and T, right? There is the resulting surface. You can talk about the partials with respect to those parameters. Those will always be tangent vectors. You can compute your capital N vector as the cross product of those, right? Now, observation, when you have a vector, right, vectors have a direction and a magnitude. Both of those are going to be useful in this situation. So I'm just going to point out that the direction is this little vector. That's a unit vector, of course, being the direction. Unit vectors, this is a normal, so this is a unit normal vector, it also, just saying, comes from the parameterization because it comes from the parametrized normal vector, right? So I'm going to be referring to this as the parametrized unit normal vector. Okay, just a little bit of language. Let's see here. The magnitude, of course, we've already talked about what the purpose of the magnitude is. The magnitude is our stretching factor that allows us to get our hands on how big little pieces of area are. And, of course, we also have, let's see here, this formula for capital N is this cross product. Now, here's the one little new thing I'm going to introduce here. The one little piece of additional information I'm going to point out is that you can expand this out in coordinates. Now, nothing happened in this equation, right? I mean, I literally just writing out these partial derivatives with all the coordinates, x, y, z, expanded out. And then you can perform the cross product, and again, nothing happened here. I didn't really do anything. I just multiplied out the cross product. And as it turns out, and I think this is an eyebrow raiser, each one of these coordinates of our capital N vector you see here, keeping in mind all of this is capital N, each one of the coordinates happens to be, and you got to write this down, you got to work out the little details, check it for yourself, confirm that this is right. They happen to be seemingly two-dimensional change of variables stretching factors. And what are the odds, right? That seems very surprising. I didn't see this coming the very first time I saw this. Like I say, it's an eyebrow raiser. It makes you suspicious that maybe there's something going on, that maybe this isn't a coincidence, maybe there's a good reason why these are two-dimensional change of variable stretching factors, and in fact it is not a coincidence. There is a really good reason why these are those, and I wish we had time to talk about it. We don't. I'm sorry. If you're curious, come to office hours. I would very much enjoy showing anyone who's curious. Yes?
Just to clarify, the lowercase vector is just a normalized.
Yes, it is a normalized normal vector, which is, I'm going to say, a little bit of unfortunate terminology, but it's the unit. It's the unit normal vector. Yeah, exactly. Parametrized unit normal vector, and that'll end up being important later. Okay. All right. Now here's a special case. I emphasize this is a special case. This is not a general tool. This is not a general alternative. This is not a substitute for what we just did. This only applies in a special case. Sometimes you are using not just a regular parameterization. Sometimes you are using a graph parameterization. Now you see here our surface. This surface here is described as a graph. And if you are using a graph parameterization like so, here's the thing. That always looks like this every time. That's how the graph parameterization works. If z is a function of x and y, that's what the graph parameterization is. This is what the partials will look like every time. This is what that cross product will look like every time. This is what the magnitude ends up being every time, right? So this is a good additional formula to have in your toolbox. Save you having to crank out this little process every time you want to use a graph parameterization. Perfectly reasonable. Just cite. Anytime you're using a graph parameterization, my parameterized stretching factor, boom, this formula right here. You just have that locked and loaded, right? Totally fine. You can just go with it. Right? Again, reminder, warning, this only works if you are using the graph parameterization, which only works if your surface is a graph, specifically. And the function whose graph you're looking at, that's the function whose partials are being referenced right there. All right. Now, there's a lovely application of this. I think this is a really cool idea. I like it when multivariable calculus becomes just, really grittily useful in the real world and like everyday senses, right? Of course, all of this multivariable calculus is extremely useful in some way or another in engineering. Yeah, that's obvious, right? But day in, day out, home life, useful, right? And this comes up a few times. So I'm going to make this observation that pair of terms is the magnitude squared of the gradient, right? And don't forget, the magnitude of the gradient says how steep is the graph. Flashbacks to chapter 2. So, neat fact then, if you are looking at a graph, right, then your area stretching factor only depends on how steep is the graph by this particular function, this particular expression. And here's a way that you can apply that. So someday y'all may own a home, and if you do, someday you may have to put a roof on that home. And get ready, that's going to be expensive, right? Like a lot, like 10 grand. It's a lot of money. Very, very expensive. I would encourage. Now, this is personal advice, right? I encourage that you don't just trust the roofing company to do all the computations accurately, because a little oopsie here and there, that could amount to several $1,000s. And why not double check, right? Turns out it's easy to do. So one of the big expenses when you put a roof on is that you need to know what the area of the roof is. And of course the area is, you can see, it's made up of a bunch of polygons, and most of these polygons are not, squares and rectangles and right triangles, nice, convenient things like that. And the edges that you would need to understand in order to compute them, right? I mean, how are you going to compute that length? You're going to climb up on the roof, right? The top of the roof of my house is something like 40 feet off the ground. I'm not going up there. I fall. I'm not doing it. Pass. So how are you going to measure that? And then, of course, you have this huge geometry problem of how to, once you have all the measurements, none of the angles are right angles, how do you compute the area? Right? This is a nasty problem. So the way I suggest is that you realize that your roof is a graph in it. Right? Z is a function of x and y. It's a graph sitting over a much easier to describe region. Right? That footprint area. Highly accessible. You just walk around the outside of your house with a tape measure. No big deal. Super easy to measure. Super easy to do the geometry. Mostly right angles. Right? And all you need to know in order to compute your stretching factor here, and of course now your stretching factor is the thing that's going to be your integrand. Convenient little fact, and I don't. I'm just going to assert that this is the case most of the time. All exceptions granted. But how steep the roof is in most houses, mine included, approximately constant. Pretty much. I don't know why, but that tends to be the case in most houses. So if your steepness is constant, that means your stretching factor is constant. That means your stretching factor will pop right outside of the integral. All you're looking at then is an integral on your pullback space of 1. Namely, your pullback integral is just telling you the area of your footprint, and that area of your footprint is easy. Again, rectangles. Right? So this represents a really, really easy way to compute the area of your roof, and all you need to know is the steepness, and that steepness is actually pretty easy to calculate. The way you compute that is you go up into your attic, right, and you pick a there's going to be some, I forget what they call these things here, rafters or something. You pick one of those, and you just go up there with a level and a yardstick, and you can just rise over run, find that slope, the steepness, the stretching factor, and multiply by the area of the footprint, and that tells you what your area is. Pretty straightforward. Does everybody follow that example? All right. For whatever it's worth, I'm a double checker. I've checked up on this, for example, in our house when we had a roof put on, and likewise all the financing, when we took out the loan to buy the house, right? I just double check everything. It's one of the nice things about knowing how to do math is you can double check the calculations that they do. And let me see now. I have caught 4 or 5 mistakes that have been made, right, over the course of the however many years. And I think the total amount of mistakes that I've caught. Oh, by the way, coincidentally, what are the odds? Every mistake that I've caught has been in their favor. Isn't that weird? I've never caught them undercharging me, not even once. It's weird. Anyway, it's something like $6,000 or $7,000. I don't remember the exact numbers, but yeah. So anyway, for your consideration, something to think about. Okay. Alrighty, so that's 7.1. Let's move on to 7.2. Let's see. I am going to point out first that sometimes you want to add stuff up over a surface. All right, let's talk about different kinds of integrals we've talked about. We've talked about single variable integrals, double integrals, triple integrals, various integration techniques. Not really different integrals, just methods for computing. We've recently discussed line integrals. Now that came in 2 forms. There was scalar line integral, and then there was vector line integral. Right? So we've got 5 different kinds of integrals that we've written down. Basically 5 different kinds of Riemann sums to address 5 different kinds of scenarios where ultimately we're all kind of doing the same thing, where we take a hard problem, we chop it up into little pieces, then we want to add up the results. Okay? So here's number 6. Suppose that the thing I want to chop up, where I want to do an accumulation argument, where I want to argue that the whole is the sum of the parts, chop it up, add it up, however you want to say it. Suppose that's a surface. Can't call this a double integral. Double integrals happen in the plane, and they don't account for the domain being curved. Can't call it a triple integral. There is no volume. We are not currently armed to be able to address a situation like we do not have an appropriate Riemann sum, aka an appropriate concept of an integral that would apply to a situation like this. And so we're just going to write down a new one. There's nothing creepy. Here it is. If you're adding up whatever it is that you're adding up, maybe you're interested in how much mass there is on this surface. Maybe this surface is the side of a hill that has weeds growing on it, and you want to count the total number of weeds. I don't know, something like that. Well, you chop it up into little pieces, and then on each individual little piece, you're going to make an argument that's going to look approximately like this, which is you're going to say whatever the stuff is, whatever your quantity is that you're interested in, you're going to talk about stuff per unit area times area. Right? That's been our approach all the way along. It's always stuff per unit size times size. So that's what we're going to do here. Stuff per unit size times size. It's just that now size, in this case, means area. Specifically, area on the surface. Okay. Now, I am going to flash us back here to when we did something similar with curves, right? You'll recall that we, again, when we first looked at line integrals. We were looking at a curve in space, and oh my gosh, how are we gonna make an accumulation argument on a curve? Well, chop it into little pieces, and here it was stuff per unit length times length. It really is very analogous here. Stuff per unit size, stuff per unit area times area. Very, very similar. I went to a little bit of effort anyway to lay it out on the page very similarly, right? To emphasize how analogous this is, right? So I just want to point that out, and we're going to make an analogous naming convention here, very standard. So this is an integral, just like that's an integral. This integral is over a surface, analogous to this being an integral over a curve, right? But it, broadly speaking, line in the liberal sense of the word line, right? And, we had to throw in this term scalar line integral because there turns out there was another kind of line integral that came around later, right? And likewise, we're going to call this a scalar surface integral because we are very soon going to see another kind of surface integral. So again, I have to modify, specifically call this a scalar surface integral. So note the analogy. I think that's really strong. I'm a big believer in analogies, right? When you make the realization that all we're doing here is the same idea as what we did here, just adapted, that these are two-dimensional surfaces instead of one-dimensional curves, and they have areas instead of length, and it's pretty much the same thing. Adapted. Okay, and then likewise, how did we actually compute scalar line integrals? How can we kind of steal that idea? Well, we used parameterizations of curves, and we pulled back through the parameterization. Likewise here, how are we going to compute scalar surface integrals? We're going to parameterize the surface, and we're going to pull back through that surface parameterization. Everybody see how we're just same thing, right? Same basic idea. Okay. All right, let's see. Let me get back at business here. Again, with the good news, we already have everything's in place. We already pretty much have what we need. If I write down a scalar surface integral like this, I'm going to need to know what's the surface area of this little piece of surface there, and I already have that formula. The surface area relates to parameter area by way of a stretching factor that we have already computed. That stretching factor is the magnitude of capital N, and so that is what allows me to compute ds. Totally analogous to the line integrals. And we're in business. We have a new kind of an integral, right? Scalar surface integrals. We have a new formula for how to compute them. We compute the stretching factor and pull back through the parameterization. It's a lot of the same stuff. Different details appropriate to the different geometry. Same basic idea. Example to follow. Is everybody with me so far? Okay. All right. Let's see, where am I? Here we go. So again, a real quick observation that you look at this formula here for how we compute our scalar surface integral, and there is some concern initially over the fact that, I see my parameterization there. This formula seems to depend on the parameterization. By the way, I also see it there, and keep in mind all of this is in my integral as well. So the parameterization is a pretty prominent participant in what this integral is, I'm worried about the fact that different parameterizations might make different integrals that might give me different answers. And again, good news. It turns out that never happens. The integral is completely independent of what parameterization you pick. Proving that is a bunch of trouble. That's in the book. Curious, it's not what this course is about. Don't worry about it. I'm just going to assert and ask you all to trust me, and I think it's a pretty believable result. That parameterize however you like, doesn't matter. Okay, so y'all will recall that my first example that I did, I guess I can flash back, come to think of it. First example that we did with scalar line integrals was something like this, where I described something modeled by a curve, parameterized curve, and pointed out that, yeah, you just pull back through the parameters, plug and chug. It's really very much plug and chug, right? And again, you're going to notice with the layout here, same thing here. If you have a surface, and if you can parameterize that surface, thankfully, we now have a toolbox full of tools for parameterizing surfaces, right? We know how to parameterize a lot of surfaces anyway. Then, just like here, you compute the stretching factor. Just like here, compute the stretching factor, and then plug it in. Right? The flow of these examples here is structurally, morally equivalent to the flow, the big picture over here. Different details, of course, obviously, right? But same basic ideas. And so, for example, we'll just take a quick look at one of these. If you want to compute the amount of mass distributed over your surface, you want to compute the mass distributed over your surface? Well, the whole is the sum of the parts. Right, that's how mass works. Mass is an accumulating quantity, thankfully. On any little piece, mass is mass per unit area times area. That is surface area. We have our stretching factor formula, that the stretching factor, which, again, y'all can compute and confirm. It depends on the parameterization, of course. But stretching factor tells me how to compute surface area in terms of parameter area. Pull back through the parameterization, and lo and behold, you've got yourself an integral that you can compute to tell you what you want. So, again, very plug and chug, and the other examples here on the same page are totally analogous. Okay, so I encourage you all to look through these examples. And I'm going to move on now to where things get a little different. Before I do that, though, let me go back to here, where we're talking about line integrals and where things got a little different. I'm sure you all recall. It's because we were looking at work. And we have this formula for work. It's force dot displacement. And, we went into this with an open mind. Work is force dot displacement. You can write that down. Weirdly, we just end up with a different kind of integral because, there it is. And the integrand is a vector. And the differential was a vector. And that was just strange, right? Just kind of a different critter. Okay? And we gave it a different name. That's what we call the vector line integral. So vector line integrals came out of trying to apply scalar line integral ideas to this one specific application, work. And then it turns out that the construction we created has other applications, right? But it all came out of one specific application. That was work. Well, the same thing's going to happen with surface integrals. It's just not work that's going to be that specific application. As it's going to turn out, the specific application we're going to be interested in is flux. Now, quick flashback. Y'all remember we talked about flux back in Chapter 3. And the big idea is that flux is this expression. Why do we care about this expression? Well, because it tells us how much, in whatever sense, how much fluid per unit time is moving through your surface. And depending on how you set up your vector field, it's either going to tell you volume per unit time or quantity per unit time, whatever, right? You got a lot of options on how you can set up your vector field, and correspondingly you get different interpretations of flux. But in all cases, independent of however you set it up and however you interpret it, this formula for flux is an object of interest. Okay, and I'm sure you all remember that the argument here for where this came from comes out of looking at this diagram and just, kind of getting in there and getting your hands dirty and computing. That's the formula that pops out. I do encourage, this would be a good time to go back and think that stuff through again, make sure you understand all those little details. Okay, well, of course, this only works if your vector field is constant, right? So we need the flow to be constant over the entire, I can't draw straight lines, but we need the vector field flow to be constant over the whole surface. And we also need, for this to work, right, critical to the calculation that we did, we assumed that the surface was flat, because we argued that that the resulting volume of water, however you want to describe it, is actually a parallelepiped, and that's just how we got our foot in the door on the computation. So constant vector field, flat surface. And what we're going to do now is just ask, what if it isn't? Right? How do you deal if you have a curved surface? That formula above, out the window. Can't use it. Doesn't work. Doesn't even make any sense. Nonsense. And again, what if our vector field is not constant? What if our vector field is different in different places? And by the way, that's pretty real world, right? If you're interested in fluid, that moving in some scenario, fluid flows depend on where you're looking, right? So the big idea, and you can probably see this coming, is we chop it up into little pieces. That's what we do in this class, pretty much, right? We take big problems, we chop them up into little problems, and on the little pieces, that little piece is approximately flat. Over that little piece, because it is little, the vector field is approximately constant. And so on each little piece, we're going to be able to do a calculation based on the formula we already have, and then we're just going to add up over the entire surface. And we'll pick up there next time. See y'all later. Have a good rest of your Monday. Oops, I hit the wrong button there. Okay. Don't forget about attendance. Whoops.